Now we are putting the introduction. What is CRO? CRO was partially in our IGCSE also. CRO is basically is a display device used to show variations in form of waves. CRO is a display device used to show variations in form of waves. Like this is like a monitor. Look, this is the outlook of a CRO. This is the outlook of a CRO. CRO is like a monitor. May God not, if you have to go to a hospital and you see the patients which are on treatment, they have a CRO, they have a monitor with their bed. This monitor is showing the blood pressure and any many other things. This is called a CRO. Similarly, the radars used in the military purpose, they also use this. Now, this is a famous heart pulse shown by the CRO. CRO is a display device. This working is not in course. How CRO work itself is not required now. We had a major syllabus changes in 2016 and then major syllabus changes in 2022. When you do past papers and you go till 2010, you had two syllabus changes junction, and you should know what topics are not there because it will save your time, because obviously some topics have been removed, like a whole chapter of electric field has been removed. My second concept, CRO is very accurate. CRO is actually used when you need to measure, when you need to determine a small number to a very high degree of accuracy. For example, time of fall of a ball. When a ball is falling down, when a ball is falling down, when a ball is falling down, it takes a very little time to reach the ground. Now that is a very little time. CRO can measure this much accurate small numbers. CRO has few applications, like it's a display device, as I had explained, like the monitor doctors use to check the different readings. Second, to show a change as a waveform, like the musical instruments, their output on a screen. As a timing device, like it means it's a digital, it's like a clock, it's like a timing clock, and it is very accurate. It is used as a voltmeter. CRO can be used as a very accurate voltmeter. We have voltmeter, but this is much more accurate than that. Readings and calculations. CRO should be considered as a graph. When you take out a graph paper, you can make a scale on it, like 1, 2, 3, or 2, 4, 6, etc. CRO is like a digital graph paper. CRO is like a digital graph paper. This is the outlook of a CRO. This is the outlook screen of a CRO. It's like a digital graph paper. Now I show you that CRO is basically a display device. Now look at this. This is now this is a very good website. It consists of simulations. What are simulations? Actually, they help you to like a laboratory, like a working in a laboratory, and this is a very good website which shows multiple simulations in physics, in chemistry. The benefit that you can change the values, like if I change the reading now, look at this, I'm changing the value, frequency and period, the time period I mean. Okay, now look, I'm switching on it, it's off. Now I make it at 10, then I make it, let me decrease the frequency. Now, look, this is the output on the screen. I decrease the scale further. Now the graph is more readable. I decrease the sensitivity further. I'm decreasing the scale. Now the graph is quite readable. This is called calibration. This is necessary for any graph paper. When you take out a graph paper from a screen, when you take a graph paper from a screen, from a graph book, you have to scale it. And this is what I'm doing. Now I decrease the scale further. Now it's too big. So now this looks better to me. I can go back. I can look. Now it is so shrink that I can't see it. So this is called calibration. So CRO needs to be calibrated just like a new graph paper has to be scaled 0, 1, 2, 3, etc. And then you can take reading. Now this is the scale on time period. So time period and frequency go together. Now peak voltage. Peak voltage is actually, voltage is always on the y-axis. Now voltage is always on the y-axis. Look at this. Now this is the voltage. Let me give some signal here. This is the signal. Look at little graph is there. Now I'm decreasing my scale sensitivity. The graph is getting bigger. Graphs always work opposite. Small scale gives you big graphs. Now look, this is quite readable. Now it's going out of scale. Now this is the suitable output. This is how CRO works. CRO has two buttons, two knobs, which control X plates and Y plates. You can control the size of the graph by moving the knob. You can see it is written volt per division. Voltage is on Y axis and current and the time period is on the X axis. Now, this is how a CRO works. A CRO is a display device. It is like a digital graph paper. Its y-axis is voltage and x-axis is time. So after giving the heading CRO, you have to mention that CRO common readings are time period, frequency, and peak voltage. Time period, frequency, and peak voltage. So in our course now, they give you MCQs where they want you to read these things: time period, frequency, and peak voltage. So after giving the heading CRO, you have to copy this.
Done, sir.
Now, what is frequency? Number of cycles upon time in second. Time period is equal to 1 upon frequency. Peak voltage is the amplitude. We have to copy this also for a scale reference.
Done, sir.
Right.
Yes.
Now, look at this graph. We look at this graph. It is time period. Look at this graph. It is time period on x-axis, voltage on y-axis. 1 second is given to be 10 power 3 millisecond. This is how you have to remember these questions. Now, let us try an example. This is my graph. No need to copy the graph because this is actually a practice on the screen. X-axis is 2 millisecond per division. Y-axis is 5 millivolt per division. Okay.
So
Now,
the voltage will
hmm,
be 10 volts.
the voltage will be 10 volt. Good. And what about time period?
It will be 4 seconds.
For
4 milliseconds.
milliboxes.
4
Time,
milliseconds.
the time period is still here. Okay, this is time period 1, 2, 3, 4.
8 milliseconds.
Good. You got it now. Time period is 8 millisecond, which means 8 into 10 to the power minus 3 second. Frequency is equal to 1 upon T.
Frequency will be frequency will be 125.
Hmm. This is how we work out. So now method, what is the method? Count the divisions and multiply, count the division, count the divisions and multiply with the scale. CRO being a digital graph paper needs calibration. You always need to calibrate. This is the outlook of a CRO. It has two knobs, X and Y. It has two knobs, X and Y. So you can control the CRO, you can control the CRO from these two buttons. You can, which I had shown you in that animation. Now, this is the output of the CRO. This is another question. Now, give the heading digital and analog. Let me share the, give the heading digital and analog. Let me share the CRO link so you can practice CRO calibration. And I have stopped the screen share just to um, I have stopped the screen share because I have to make some sharing here. So I'm sharing you the CRO, and this website is very good. It's a simulation website, but limitation is Windows. It doesn't work well on our Android systems. It works good at Windows system. So let me share it here if I can get. No, the link is. I have shared the link, and now we can open the discussion on digital and analog. When you talk about digital and analog, whenever you talk about digital and analog is always two versions of our digital and analog are always two versions of our elect devices, measuring devices. I think you remember that in O level, and now in A level, even you have seen the lab, 1 year caliper, micrometer, screw gauge, and the especially that clock, the normal clocks, the stop clocks, they all are available in two common versions, which are called digital and analog. A digital device like a calculator has a display. A digital device has a display. A digital device has a display. A digital device has a display. Look, this is a digital device. This is a digital device, and this is an analog display. Analog devices like this one has a needle and they have a printed scale. Digital has no printed scale, it has a screen. Now, digital instruments have a display, analog instruments have a scale. So, after giving the heading, you have to copy this concept. This is again a very rare topic. It doesn't come much. Some topics come very oftenly. Some topics are rare. So this is one of some rare topics are there.
Done, sir. I wrote it.
Good. Now, digital devices, this is an analog scale. This is a digital device. Digital devices like this one is very accurate. The main advantage is that you can measure, you can read up to 2 decimal place, 3 decimal place, even 4 decimal place. This is the advantage. This is the advantage. You can read for multiple number of decimal places. You can read multiple number of decimal places, but there is a problem in digital devices. The digital devices work on a coding or a program. Now, this is a problem sometimes because if the coding fails or the coding is not working correctly, this is called the coding error, or the battery gets weak, the current is not full. So like a rechargeable device, it can give you wrong answers. Analog devices like this, analog devices are not that much accurate. Analog devices are not that much accurate, but they are very reliable. So what's the summary? Digital
Uh,
devices, yes, go ahead.
Digital devices, they're very accurate, but if there's a coding error, they will
Hmm.
give wrong values. And for analog, you can't be accurate. You can't be precise with the values.
This is, you got the right point that digital devices are accurate but less reliable. Digital devices work on a virtual interface. Digital devices work on a virtual interface. They have a screen which is actually not real. It's actually a LCD or LED screen. So now we move forward to our next title, types of error. Give the heading, types of error.
Done, sir.
Now there are two famous types of error, random error and systematic error. Now, we have a concept here in a laboratory that when you are working in a laboratory, two types of error can occur. Some are called silly mistakes or fluctuating error, which always can go any number, like rounding error, wrong calculation, wrong formula, parallax error. They are called random error. But some errors are there, which are fixed. Some errors are there which are fixed in number, like zero error. Like if your watch is 5 minutes ahead, it's a permanent error. So if the error is permanent, it is a systematic error. If the error is fluctuating, it is random error. So there are two types of error. Now, random error is that which can be any number, which can fluctuate. So random error is not fixed. Now, this is how random error looks like. On a graph, random error appear as crosses. The crosses are jumping up and down. Look at this diagram.
So random errors are not fixed. They can keep changing.
Example, in maths, if you do a mistake in writing the formula or you apply a wrong calculation, then it is called a random error. Actually, random error is any error which takes different values over time. Maybe it becomes 2, maybe it becomes 3, maybe it becomes suddenly 100. So this is an error which is arising from fluctuation. So they can take any number.
Okay, I got it.
Examples are parallax error, which is a very famous O-level physics paper 6. This was in our ATP also. This is a very famous error. How we can avoid parallax error?
We have to look at perpendicular. We have to look at the object perpendicular to eye level.
Yes. Weighing machine fluctuates.
So to prevent random errors, do we take average or do we continue repeating the experiment?
Random error can be minimized by averaging.
Okay.
Now this is, look at this, another random error. Now this is the concept you were discussing. Averaging the result using multiple measurements minimizes the random error. Observe this, absorb it.
So to minimize a random error, we repeat the experiment and then we take average of the values.
Yes.
Okay.
Systematic error. This is a constant error either on the higher side or on the lower side. Look up the definition, systematic error.
So systematic errors will be precise.
Precision is a different word, but indirectly it's right. How it appears?
As a straight line graph.
No, it appears as an intercept.
Sir, what is intercept?
Cutting any axis.
No.
If it cuts an axis, it means
It's
it
not.
has a, it is
Is it?
having, it is cutting x-axis. It's not passing through origin.
Oh, okay.
If it is not passing through origin, then it's a chance
That it will be a systematic error.
yes.
So random errors will produce a scatter graph and systematic errors will have an intercept graph.
Yes, perfect. Typical causes of systematic error, look, observational error, imperfect instrument, environmental interference, theoretical error. Zero error is the most famous example. Any error which is fixed. Theoretically, do not just like people sometimes make a memory. Okay, fine, zero error is systematic. No, this is not the way. If zero error fluctuates, then it is not systematic error. It can be random error. Even people have a famous perception that parallax error is a random error. That's a wrong perception. Parallax error is random only when it fluctuates. A systematic error cannot be eliminated by averaging. Now, these are the two types of error. I will share this just conceptual sheet so they can be recorded. Now give the heading, accuracy and precision. Give this heading.
Sir, so there is no way to fix systematic error?
No, officially not.
Okay. Done, sir.
Just for example, your watch is 5 minutes ahead and you can't fix your watch. It means it's a systematic error. You adjust it. You
Oh,
can
okay.
adjust you can adjust it and you say, okay, fine, whatever answer you are getting, subtract the error from it. This is how we can say. So we have a concept, random error can be reduced by averaging. Systematic error cannot be reduced, it can be adjusted. Acha, accuracy and precision. What is accuracy? It is the
Uh,
extent which average measurement is close to the actual value.
Not accuracy is the average value.
No, accuracy is always measured from the average value.
Oh, okay.
For example, I have I have three readings. I have three readings for G.
So I will find the average of this value, and then if it is close to the true value, we will say that my readings were accurate.
Yes. If the average is close to the true value,
Okay.
look up this formula.
So why do we need to calculate like percentage error?
Because it will tell you the accuracy.
Okay.
Because it will tell you the accuracy. There is a tolerance level within which accuracy or error is acceptable. For example, percentage error is equal to error upon true value. So we have a tolerance level of around 10 to 20% in which the system consider it accurate. 100% accuracy is obviously not possible in a lab.
I got it, sir.
What is precision?
Precision are values which are close together. They don't have to be near the true value, but the values that you take should be close. So like 2, 3, 5, and all.
And maybe they're not accurate.
Yes, they don't have to be accurate,
Like
but
G is
the values need to be close by.
and there is a level of closeness within 10 to 20%. They should fluctuate. This is called precision. A precise but inaccurate result may be due to systematic error, which you were asking at that point. Now comes to the main title, the last title here, and it is the third most important title of this big chapter. Give the heading uncertainty.
Done, sir.
This is the symbol. What is uncertainty? It is called a no, it is called a known error. Look at this.
Plus minus 2 is the uncertainty. It's the estimate between the true value and the actual value.
Good. Uncertainty is the best example is the marking scheme, which write answers like that. Uncertainty is the known or expected error in a measurement. Uncertainty is always given correct to.
One significant figure.
There are three types of uncertainties: absolute uncertainty, fractional uncertainty, and number three, percentage uncertainty. You have to copy this list.
Done, sir.
Good. Look at this example. 30 plus minus 1.
My one is the uncertainty.
Yes.
Sir, will there ever be a question where we will have to determine the uncertainties in paper 1 and paper 2?
Obviously, uncertainty questions are very common.
Okay.
Uncertainty is a very common topic. In MCQs, it appears many times. What happens if uncertainty is given in percentage?
It can be written as a fraction.
Hmm. Uncertainties should not be subtracted. They should not be raised to a power. We should avoid changing the unit conversion, doing the unit conversion on uncertainty. Now, it is always better to modify a formula. For example, if diameter is given and you are dealing with area, so we can use this formula that A is equal to pi r square, but we can also update the formula and involve pi d square upon 4. Area is equal to pi r square. This formula was very common in O level, but in this chapter, you will see this formula a lot. Why? Because normally data contains diameter. We do not include the constants during uncertainty. So when it is written pi upon 4 d square, you will consider it as simply d square. Uncertainty calculations. The first one, sum and difference. Rule number 1, if u is equal to x plus y, this is the formula, then deba u is equal to plus minus deba x plus deba y. Copy this.
Sir, can you explain this?
I'm going to explain it. First, you copy it.
Done, sir.
So u is equal to x plus y. What this formula means? This formula means if two quantities are being added, if two quantities are being added, their uncertainties are also added. For example, look at this question. M1 is 20 plus minus 2. M2 is 30 plus minus 1 kg. I want to find the total mass. So how this formula will be applied? Because I need to find the total mass. Total mass is equal to sum of the two masses. Look at this. How I find the total mass? M1 plus M2, 20 plus 30. Look at this one. And how I find the uncertainty sum? It will be 2 plus 1, 3. So I will write the answer as 50 plus minus 3 kg. This is formula number 1. Look at this working, and you can now you can ask the question if you have.
No,
Simply
no,
add.
no, I got it.
Hmm,
Sir, we can only add them if the units are same.
definitely.
Okay.
Rule number 2. Copy rule number 2.
Done, sir.
R is equal to external radius. Small r is equal to internal radius. T is equal to thickness. Now, this is the formula. No need to copy the question. Just look at it orally and find the thickness and the uncertainty.
Sir, the thickness will be 9 and the uncertainty will be plus minus 3.
Now, copy this.
Done, sir.
How we write this formula, for example, it's a product, Ohm's law, famous formula. V is equal to IR. Now, you will write delta V upon V plus minus delta I upon I plus delta R upon R.
So when two quantities are being multiplied, we add the fraction uncertainty. So we do the uncertainty divided by the value and then we add the other one.
Hmm. So we we actually make fraction for all the variables. Like for example, P is equal to VI power. So delta P upon P is equal to plus minus delta V upon V plus delta I upon I.
Okay, I got it.
This is how we write down the uncertainty formula. So when they are in a product form, their fractional uncertainties are added. Look at these two examples. Area is equal to length into width. Volume is equal to length into breadth into height. Power is equal to VI and F is equal to MA. All these type of formulas are to be converted into fractional uncertainty. Now, if you want to find the absolute uncertainty, you will move the denominator. Look, this is the denominator. You move the denominator to the right hand side, you will get the absolute uncertainty. So if you want to find the absolute uncertainty, you will move the denominator to the right side. Area is given is 20 plus minus 2. Area is length into breadth. Now you have to try this question. I'm just coming in a minute. Try this question.
Okay.
area is coming 300, and now uncertainty. If you have found the uncertainty, let me know.
It is the fractional uncertainty will be plus minus 1 by 6. Oh, wait. No, plus minus 50.
Hmm.
Sir, if we don't want to find the absolute uncertainty, we will leave it in fractional form.
Uncertainty. Uncertainty should be a number.
Oh,
Un-
okay.
Hmm. Uncertainty should not be left as a fraction. Now, if three variables are being multiplied, you will put three fractions. Like this is a question. Volume is equal to length into breadth into height. So you have three variables, three functions. You first multiply them. Then you apply the formula on this big expression. You will be using the same approach for absolute uncertainty. You will take the denominator to the right. Now, u is equal to x upon y. Division is treated very similar to multiplication. U is equal to x upon y. Deba x upon x plus deba y upon y. You have to copy this. Number 5.
Done, sir.
This is called fractional uncertainty for product. Now, for example, density is equal to mass upon volume. Now you have to solve this question. You need to copy the data. Yes, you have to record it. Density is equal to mass upon volume.
The density will be 4
Density will be 4.
and the uncertainty will be 0 point. Should we multiply the denominator or?
No, but you have to take it to the other side. Look at this working.
Yes, even I got 0.18.
Hmm.
Sir, uncertainty will always have to be in one significant figures.
Uncertainty always be.
One significant figures will always have to round it.
You always have to round it.
Done, sir.
So multiply and division go together. They have a common approach. They have a common approach. Now, raised to a power. When something has a power, then u is equal to x power n. So power becomes the coefficient. Power comes back. This is number 7. Copy the rule.
Done, sir.
Okay. Like, for example, y is equal to x cube. Now look at this example. Cube x is equal to 20 plus minus 1. I need the volume. Now you have to try this example.
Hmm. Sir, will the uncertainty be 0.2?
Uncertainty will be, first you find the volume.
8,000.
I'm getting
multiply.
1200.
Say even for power, we'll have to bring the denominator.
The power has the power comes back, na?
Okay. Yes, I understood.
Okay. $1,200 will be written as 1,000 for the rule of for the rule of how many significant figures? For the
Significant figure.
now these are the questions where you have to remember that power